Okay, so the last section here of chapter 6 is going to be where we take all of the information that we learned in the chapter and apply it to explaining the behavior of molecules. And specifically, what we're going to be looking at is taking a look at what are known as intermolecular forces, which we often abbreviate as IMFs, right? So intermolecular forces, which we can describe as the forces of attraction between molecules. Okay, so we're looking to see what sorts of forces actually keep molecules together. So what types of forces keep molecules close to each other, right? So we're looking, and this is key here, it's the force of attraction between molecules, not covalent bonds, right? That actually is a force happening inside of the molecule, so not covalent bonds. So intermolecular forces are going to be inherently weaker than stronger forces like covalent bonds, but they're going to be important because they're going to influence important properties or characteristics such as melting points and boiling points for substances. All right, so that's why we're going to take a look at them, because they are important in explaining some of the physical properties of substances. The other important reason is because we had gone through all these steps to determine whether something is polar versus non-polar, because that will allow us to figure out the type of intermolecular force occurring between molecules. So the first type we're going to take a look at are intermolecular forces known as dispersion forces. And dispersion forces are considered the weakest force of attraction between molecules. Okay, these are present between all molecules, even between your fingers and the pencil you're holding or your pen that you're holding, between your glasses and your forehead, for instance. There are intermolecular forces between every single type of molecule. But where they tend to predominate, or where they're going to have a big effect, is so they have a measurable effect. Measurable effect between non-polar molecules. Right, so we find these dispersion forces. Sometimes they're called London forces, between everything, but they're going to be especially important between our non-polar molecules, right? These are the only forces actually that we find between non-polar molecules. So the only forces present between non-polar molecules, right? And the key thing here is they are very, very weak. The second type of intermolecular force is known as a dipole-dipole attraction, right? And the name kind of gives it away in terms of what is needed in a dipole-dipole attraction. Dipoles must be present. All right, specifically polar molecules. Must be present. Right, and these dipole-dipole attractions, they are stronger than your dispersion forces. So for example, if you have something like HCl down here, right, we know now that HCl is going to be a polar molecule. We have one end of it that is going to be slightly positive, and the other end, the Cl end, that's going to be slightly negative. So if you have a neighboring HCl molecule, right, one would predict that the slightly positive end of that one will be oriented close to the slightly negative end of the neighboring one, right? Opposites attract, and that attraction between them is what this dipole-dipole attraction is, right? So it's attraction between one dipole and another one, specifically the opposing partial charges getting close to each other. So these are a little bit stronger than the dispersion forces. The third type of intermolecular force is known as the hydrogen bond. And I'm going to put the word bond here in quotations because it's not bonding in the strictest sense, right? Really what you can think of it as, it's a very strong type of dipole-dipole attraction. It's sort of like dipole-dipole attraction on steroids. And the reason why is because of the nature of the elements involved. All right, so again, the name here, hydrogen bond, kind of tell you what needs to be present, right? So hydrogen needs to be present. And secondly, that hydrogen needs to be covalently bonded to a very electronegative element. And there are three of them that satisfy that criteria, to either an oxygen, a nitrogen, or fluorine. Right, so those are the three atoms that hydrogen needs to be covalently linked to in order for the hydrogen bond to be present between one molecule and another one. All right, so for example, if you look at ammonia, NH3, over here, right, we know that NH3 has this shape now. It looks like it is trigonal pyramidal. All right, and then we have the hydrogen present, so there it is, and it's covalently linked to a nitrogen. Right, so we do have a big electronegativity difference between these two things. So the H here is going to have a slight positive charge, and the N is going to have a slight negative charge. So if a neighboring ammonia molecules comes close to it, we would predict that the slightly negative N is going to get close to the slightly positive end of the neighboring, slightly positive H of the neighboring ammonia molecule. And that attraction between the negative here and the positive is what that hydrogen bond is. Right? Hydrogen bonds are typically denoted by using a bunch of dots, right? Just like that. Another very important molecule where hydrogen bond is important is in H2O, right? Water has a lot of hydrogen bonding between the water molecules, right? Again, it's an intermolecular force, meaning it's between different molecules. So there's my H2O, and now we know that H is going to be slightly positive and the O is going to be slightly negative. So if a neighboring water molecule comes close by, we would predict the slightly negative O here to be oriented close to the slightly positive H. So we have that attraction between them, our dots here that denote that it's a hydrogen bond. Hydrogen bond, we often use a shortcut, H bond. Okay, a very common misconception that students have is if I gave you this and I told you to point to it, or point to the hydrogen bond, a lot of times students point to that. Okay, that is not the hydrogen bond. That is a regular covalent bond, right? The hydrogen bond happens between the water molecules themselves. So not only is hydrogen bonding responsible for the attraction between water molecules, but it's also going to be responsible for the shapes of more important ones, or maybe just as important ones. And you're going to see this closer to the end of the semester, and you'll also see it in some of your biology classes. So things like DNA, right? That double helix of the DNA is actually held together by a bunch of hydrogen bonds. Also things like proteins, right? So there are lots of different structures that you find in proteins, and a lot of them are actually held together by hydrogen bonding between different parts of the molecules. The last type of interaction we're going to take a look at here are the ionic bonds, which we saw back at the beginning of the chapter. These are, we're going to refer to these as interparticle forces of attraction. So they're not strictly or technically intermolecular, but they're still sort of grouped in this general category. These are going to be the strongest of the attractive forces found in most found in compounds. And because of the really strong attractive forces, we're going to see that most of your ionic compounds tend to be solids at room temperature, and they also tend to have high, really high melting points and boiling points, right? Because they're being held together by really strong forces of attraction. So generally what we're going to see here, and the reason why we're going through this process, is we can make a general sort of statement in terms of how melting points, for instance, are affected by these attractive forces. So generally we can say the stronger the intermolecular force, or IMF, the higher the melting point, I'll abbreviate melting point as MP, and boiling point is going to be. So in other words, if you have a really strong attraction between molecules, it takes a lot of energy to break that force of attraction. So strong attraction between molecules requires a lot of energy to break, which corresponds to a higher melting point and also boiling point. So if we go back for a second, right, and we take a look at our hydrogen bond, right, this is the strongest out of the three, the dispersion, dipole, and hydrogen bond. If you were to rank those, the hydrogen bond is the strongest. So to break this hydrogen bond here would require a lot of energy compared to trying to break the force of attraction between two non-polar molecules, right? So if you take a look, we actually have some numbers to back that up. So substances that are only held together by dispersion forces, which are weak forces of attraction, have really low melting points, right? It doesn't take a lot of energy to separate them. So these actually, bromine, chlorine, and fluorine, these actually are gases, at room temp. Right, the regular temperature of the room is high enough to separate these molecules from each other and turn them into the gas phase. With the dipole-dipole attractions, we'll see that generally these have a slightly higher melting point. And if we look at the strongest out of the three so far, the hydrogen bonds, right, compared to the ones below, the dipole-dipole and the dispersion, the hydrogen bonds are the strongest out of the three. So something like water has a really high, I'm going to say unusually high, not really high, unusually high melting point, right? And that's due to the relatively strong hydrogen bonds. Then on the other end of the spectrum here, you have your extremely strong ionic bonds, right? These are the strongest forces of attraction, so they have extremely high melting points. So it takes a lot of energy to separate these ions now from each other. If you were asked to determine the types of attractive forces that are present between the substances or the particles of a compound, the first thing you have to decide is whether the molecule is polar, non-polar, whether it's ionic, or whether you can have the possibility of hydrogen bonding, right? So typically that would involve having to draw your Lewis structure. So if we look at something like KCl, right, then KCl, as you know, you can see there's a metal in there, so right away we know that's going to be ionic, right? So it's going to be held together by ionic bonds, right? That's one of the strategies we said you can use to determine whether something is ionic or covalent. If you see a metal in it, like potassium is, right away we know that it's going to be ionic. If we look at something like water, right, we just did water before, there's our Lewis structure, right? We have hydrogen present and it's covalently bonded to an oxygen. So hydrogen covalently bonded to the O. This means that we can have hydrogen bonding between one water molecule and another one. If we look at something like NCl3, we draw the Lewis structure, right, we can see that our Lewis structure is going to look like this. Put all the electrons in to be complete. And then if we look at the electronegativity values for nitrogen and chlorine, we see nitrogen is 3, chlorine is 3, so they have the exact same electronegativity, right? So this then is going to be non-polar because it's made up only of non-polar bonds. So in the non-polar compound, the only force of attraction that we're going to have between it and other molecules would be dispersion forces.